In this last lesson, in the calculus unit, we're going to start analyzing trigonometric functions using some ideas from calculus, tangents, normals, derivatives, all that good stuff. To do that, we have to go back and talk about how we can evaluate trigonometric functions. One of our biggest tools is the unit circle that you went through in higher functions last year. In this course, I don't need you to memorize it. I just need you to be able to work with it. So some quick reminders. Here's our unit circle. Okay, when we measure on a unit circle, we start at 0, and we start going counterclockwise. Okay, for each of our big things, so degrees, 30, 45, 60, and so on, or pi's, radians, pi over 6, pi over 4, pi over 3, and so on, we have ratios. We have the sine ratio, the cos ratio, and the tan ratio, and of course the reciprocal ones. A reminder on the unit circle that this would be your cos ratio for that angle. This would be your sine ratio for that angle. And if you want to do tan, you have to remember a little bit about, let's write down Sir Sixer ticks. If you want to do tan, which is ticks, you have to take the y value, which is 1, and put it over the x value, which is root 3. Or if you will, the sine value over the cos value. And so for instance, if I wanted to find the cos of 5 pi over 6, I can do that pretty quickly. 5 pi over 6 is here. This is the cos version, so I know it's negative root 3 over 2. If I wanted to find tan of 5 pi over 3, if we want to just go down here and try one, okay, tan would be my y value, which is negative root 3, over my x value, which is 1. Okay, we're going to try a couple in our lesson, but that's the basics of it. Okay, so let's go back to the lesson and take a look at some examples. So, can you find me the exact value of tan pi over 6? So in unit circle, pi over 6 is right here. So the tan of pi over 6 by ticks, so y over x to 1 over root 3. Okay, we like exact. I'm not going to worry about rationalizing things right now either. We could if we wanted to. We know how. But I'm more worried whether we can just use these functions. Okay, secant negative 2 pi over 3. So the fact that it's negative means we have to go backwards. We have to go backwards 2 pi over 3. Okay, so going backwards, this is 1 pi over 3, and a second pi over 3. So I'm looking at this one. And it was a secant question, I believe, right? Secant. We know secant is the reciprocal of 1 over cos. So if I know cos, I know 1 over secant. I do know cos. Cos is right here. Oh, sorry, wrong one. Cos is right here. Okay, so secant, instead of being negative 1 over 2, will be 2 over negative 1. Or if we want to simplify that, just negative 2. And if we try one more, cos 3 pi over 4, 3 pi over 4, 3 pi over 4. Oh, there it is. And we're doing a cos question. Cos is my first one. So negative root 2 over 2. And that one we don't have to rationalize because there's no rational on the bottom. Okay, so we've got some ways we can do this by plugging our things in forward. We can also work backwards and figure out the angles. So I'm told that the sine of an angle is negative root 3 over 2. So if I go back to my unit circle, I'm looking for sines, as in the y part, negative root 3 over 2. It helps if we remember the idea of cast. Where can sine be negative? Well, it can be negative in the t quadrant and the c quadrant. So we're looking for negative root 3 over 2. There's one of them. And the second one is right here. So my answers are 4 pi over 3 and 5 pi over 3. And again, I'm not worried about drawing them out this year. I'm just worried about can we actually use them. Okay? We're not so worried about learning them in the first place. It's more about using them now. Okay, secant theta equals 2. Now that one's going to be tough to look for. Okay, so we might want to use the idea of how about let's use cos being 1 over 2. So it's the exact same thing. My unit circle is set up for coses and sines as opposed for secants and cotangents and things like that. So let's look for a cos being 1/2. And more specifically, a positive 1/2. So unit circle, looking for cos. Where's cos positive? Well, it's in the all quadrant. And here's my half. Oops, sorry, that's where y is, a half. We want cos, not sine. Sorry, mistake. Cos being a half, that's your x. That's that one. And where else? I'm looking for cos being positive. Cos being positive, there it is, down there. The two places where cos is positive. So my answers are pi over 3 and 5 pi over 3. And hopefully this is coming back a little bit. And then the last one. Where is tan equal to 1? Now this one is again kind of tricky because I'm not really set up for tan. I can find where tan is positive by using my cast rule. It's positive in the all quadrant and the t quadrant. But if you notice, none of these are 1 over 1. Instead, what I have to look for here is where does my tan values have the same for sine and cos? Because we know that tan actually equals sine over cos. So you might notice right here, I have the same values. Root 2 over 2 divided by root 2 over 2 is just 1. And the same is true down here in the bottom left quadrant. I got negative root 2 over 2 and negative root 2 over 2. So where does tan actually come out to 1? Pi over 4 and 5 pi over 4. Okay. The other thing again, I'm not really worried about us drawing these all out all the time. I'm going to give you a unit circle. I just need you to be able to work with that unit circle to do what we want to do with calculus, which is analyze functions. Okay, let's try some problem solving. Can you solve this for me? That's something we have to be able to do in calculus because we're going to be solving derivatives in a minute. Solving trig means we want to make equations equal 0 that we can solve for known ratios. So if I look at this one, I notice that both of these functions have a sign in them. Sorry, both halves have a sign in them. So if I can common factor that out, I'll have an equation. I'll either have the equation sine theta equals 0 or 2 cos theta minus 1/2 equals 0, which we can rearrange and then create a ratio where my unit circle can help me solve. So we'll go back to the unit circle again. I'm getting rid of all the writing on here. Where can sine be 0? Where is the y part 0? Well, one of them is right here, and the other one's over here. So the first equation can be solved if theta was either 0, pi, or 2 pi, or we're going to go back and forth with degrees, usually radians, but we can also go back and forth with degrees, so 0, 180, and 360. Where can cos be 1/2? Cos is my x, it's 1/2 right there, and the other positive 1/2 is down here. So pi over 3 and 5 pi over 3. And this is the solutions to this equation, the one we started with. We have 5 different answers that make this actually come out to 0, depending on which angles we're working with. We like this because we're going to be solving equations involving derivatives, which is you have to be able to solve for angles. Okay, so let's take it to the calculus step now. I want to find the equation to the tangent of this function at a certain point. So we know we've got a function and we've got a point or a value. We can find a point. So let's figure out what's happening at f pi over 2. So we have the sine of 2 times pi over 2 plus cos pi over 2, which in other words is just the sine of pi plus the cos of pi over 2. Let's look those numbers up on our unit circle. The sine of pi is right here. Sine of pi is the y value, which is 0. Plus the cos of pi over 2. Pi over 2 is up here. The cos is the x part. So again, I need a 0. And what do I got? Hey, I got myself a point. The point pi over 2 and 0. Now we're making a tangent, remember? So to make a tangent, we need to get that mx plus b thing going. To get our m, we need our slope, our derivative, at a certain point. So yesterday we learned about derivatives of trigonometric functions. Let's give one a try. So the derivative of sine is cos of the function times the inside piece. The derivative of cos is a negative sine. Now, a better way to write this is saying 2 cos 2x minus sine x. Okay, with the 2 out front. We now have to figure out the specific slope for our point. In other words, what's our derivative at pi over 2? So we'll get 2 cos 2 times pi over 2 minus sine of pi over 2. So in other words, 2 cos pi minus sine pi over 2. Okay, what's the cos of pi? Unit circle. Cos of pi is the x part, so negative 1. So 2 times negative 1 minus the sine of pi over 2. That's the y part. So I need the 1 up there. So minus 1. What's that give us? That gives us negative 3. So now we have ourselves a slope, a point. We can make the equation of a tangent. Fill in what we know. Our slope. Take our point. 0 and pi over 2. I'm using pi over 2 as an exact value, so instead of making decimals. A plus b. So 0 equals negative 3 pi over 2 plus b. Or in other words, b is 3 pi over 2. And so our equation for this tangent at this specific point is 3x plus 3 pi over 2. In much the same way we would deal with e's and exponential functions, we'll try and keep things exact as much as possible with trigonometric functions to avoid those never-ending decimals. Okay, you guys give one a try. Same idea. You find me this tangent. Start off with the same stuff. Let's find our point. So cos of pi over 3 squared. So think of it as being squared. Cos of pi over 3. Let's clear the unit circle here. So pi over 3, and I want cos. That's a half. So I'm going to have 1/2 squared, which is 1/4. To our derivative. Think of cos squared x is the same as cos x squared, right? So 2 comes down in front, times the derivative, times the original function, times the derivative of that function, which is negative sine. Okay, we'll simplify it just a little bit to make our life easier. So negative 2 cos x sine x. In particular, I need the slope at pi over 3. So negative 2 cos pi over 3 sine of pi over 3. Now I already know what pi over 3 is for cos because we used that in our previous point. Oops, right. Okay, pi over 3, we figured it over here was 1/2, right? So 1/2. I need the sine part this time though, so let's go find the sine of pi over 3. That's this piece. So root 3 over 2. Root 3 over 2. Hey, multiply it all together. We're going to end up with a negative 2 root 3 over 4. Or if we simplify that, just negative root 3 over 2. There's the slope of our equation. Okay, I got a slope and a point. Let's make an equation. Oops. Y equals. Fill in our slope. Keep it exact. Hey, fill in our point. Our point was we came out to 1/4 when I had an x value of pi over 3. That's b. And we're going to try and keep it exact again. So we'll get 1/4 equals negative pi root 3 over 6 plus b. Looks pretty messy, right? That's okay, not a big deal. Same process. Oops. Okay, we'll bring it over to the other side. And now we need ourselves a common denominator. What can we do with these two things? How can you add them together? Well, common denominator would be 12. Okay, this is like saying 3/12 plus 2 pi root 3 over 12 equals b. Or in other words, 3 plus 2 pi root 3 all over 12 is b. It's not pretty, pretty messy in fact, but it'll work. Okay, so what's our equation? Our equation should be y equals m, and m was way back up here at the top, so we'll go get it. Negative root 3 over 2 x plus b. And b is this big messy fraction. Okay, and there's the equation of that tangent. It's really messy, nothing nice to work with, but it is our equation. All right, what other stuff can we do? Well, let's figure out, let's problem solve with some calculus. I want to know where this function has a horizontal tangent. In other words, where does my derivative equal 0? Which again, in other words, means where do I have a max or a min? But I want it specifically on the domain of 0 to 2 pi, because we know trigonometric functions go round and round and repeat themselves over and over and over again. I don't want to do that. Okay, how do we find where the equals 0? Well, let's take our derivative and make it equal 0. So derivative of sine is cos times the tan part, plus the derivative of tan is secant squared times the sine part. And that makes it look pretty messy. So we got to be able to simplify this a little bit. Now, we've talked about identities in the past. One of the things we like to do with identities is get rid of any tans. So let's turn tan into sine over cos. That might make our life a little bit easier. I can't really do much on the right-hand side here because secant is cos, and it's not going to help me cancel. But I hope you did notice that these two things will cancel. Top and bottom and multiplying, right? So we're left with sine x plus, I'm just going to change the order here to make it a little bit easier to see, sine x secant squared x. In other words, let's common factor out, oops, not a 1, common factor out a sine, and we'll be left with the 1 plus the secant squared x. This takes us back to one of those early examples where we can solve this. How do I solve it? Well, I make my two parts equal 0. Either sine x has to equal 0, or 1 plus secant squared has to equal 0. Now if we try solving this, and then we try square rooting it, because secant squared, we have to get rid of the, well, we can't square root negative 1, so this part has no solution. So the only value that makes this true is when sine x equals 0. Okay, unit circle, where does sine equal 0? Over here and over here. So 0 and pi. So our answers to this are, and 2 pi I suppose. Where does this have a horizontal tangent? 3 spots. When x is 0, pi, or 2 pi. And again, we didn't graph it. We could graph if we wanted to. At those 3 points, you'd have maximums and minimums. All right, we're going to try another one. I got 2 questions left, and then we're done this whole course. Can you find me the extreme values of this function? Well, what are extreme values? Aren't those maximums and minimums? We know how to do that. That's a derivative equal to 0. So let's take our derivative. Derivative of x is just 1. Derivative of 2 cos x. That's 2 times negative sine x, right? So in other words, we get 0 equals 1 minus 2 sine x. Or if we solve this, 2 sine x equals 1, or sine x equals 1/2. So we're going to get maximums and minimums where sine x is 1/2. Let's go find those spots. Where does sine equal 1/2? Well, one of them is at pi over 6. The other one is at 5 pi over 6. So there's 2 spots where we're going to have extreme values. Pi over 6 and 5 pi over 6. Now this time we weren't asked to just find where they happen, we were asked to find what they are. Well, to find points, we go back to our original equation and plug in the x values. So let's see what happens at y being pi over 6. We'll get pi over 6 plus 2 cos pi over 6. Now pi over 6, I can't really do much with that. I can make big long decimals. I don't really want to do that. But cos pi over 6 is a number on my circle. So cos of 2 pi over 6 is root 3 over 2. So let's replace that. Root 3 over 2. What do we get? Pi over 6 plus root 3. So there's one of our extreme points. Pi over 6, comma, pi over 6 plus root 3. Again, they're not nice points, but we're trying to eliminate decimals, if you will. We want to have just numbers. Okay, there was two extremes. The other one was at 5 pi over 6. Let's go figure what's happening there. So same procedure, 5 pi over 6. So we'll plug it in for x, and we'll plug it in for, it was 2 cos, I believe, right? Let's go back up for a second. Yeah, 2 cos. 5 pi over 6. So we'll leave this piece alone. And our cos of 5 pi over 6, and 5 pi over 6 cos is negative root 3 over 2 this time. So plus 2 times negative root 3 over 2. So we end up with 5 pi over 6 minus root 3 this time. So our other extreme value is 5 pi over 6 and 5 pi over 6 minus root 3. And I didn't ask us what kind of extremes they are. We could probably figure those out if we needed to. We're going to have maximums and minimums. But to do that, we'd probably need the decimal version. And if you wanted to, you can use pi as a number, right? 3.14. And this number here, if you punch into your calculator, that's 3.14, comes out to approximately 2.26. And the other one, punch that in your calculator, comes out to approximately 0.886. So in other words, this would probably be the min value, is lower. This would be our max value up here because it's higher. Okay, very last question. Then we're done, the entire course. Find me the intervals of increase and decrease for this function. Where is it going up and down? Well, again, calculus and derivatives, right? So if I figure out where it equals 0, I know where my max and mins are. And I know that if I make a sine diagram, I can figure out what's happening on either side of those. So derivative of sine, well, that's cos, times the cos. The derivative of cos, that's minus sine, times the sine. Okay, or in other words, I get cos squared minus sine squared. Now, I can't solve it the way it is, because there's no identity that works cos squared minus sine squared, and I can't figure which part to make it equal 0. But if I go back in our memory banks one more time, we know there's an identity like cos squared plus sine squared is 1, or any rearrangement of that. Our standard one is sine squared plus cos squared. Why not rearrange this like this? So if I see a sine squared, I can replace it with a 1 minus cos squared. Why would that be handy? Well, if we get rid of our brackets, we're going to end up with a 1 over here and 2 cos squared over here. Or in other words, if we simplify this, divide both sides by 2, we'll get 1/2 equals cos squared. And if we square root both sides, we end up with 1 over root 2 equals cos x. Now remember, when you square root things, you end up with a positive and a negative root. So I got to find all the places where x on my circle comes out to 1 over root 2, positive or negative. So cos 1 over root 2. I look at this and I say to myself, well, none of them are 1 over root 2. But we also know that 1 over root 2 can be rationalized. And on a unit circle it is. So I need to look for where cos is root 2 over 2. Here's one. There's a negative version over here. And there's another negative version over here. And the positive version over here. So all the over 4s. So my answers for x are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, but notice they've given us a domain. So I start writing down my first two, and then I realize, well, those aren't bigger than pi necessarily. Which ones do I really want? I only want the ones that are after this. That's where pi is right there, right? So my answers aren't these two. Actually, only the last two, the 5 pi over 4 and the 7 pi over 4, based on the domain that they've given us, the part of the graph we want. So we asked for increasing and decreasing. Let's make ourselves a sign table. Less than 5 pi over 4, between 5 pi over 4 and 7 pi over 4, and greater than 7 pi over 4. Let's take our derivative and see what happens. Okay, let's pick a number less than 5 pi over, oh, but be careful here. We're on a domain, right? A given domain. I can't go over to 0. We're starting at pi. Okay, I need a number between pi and 5 pi over 4. Any number I want. So if we look at a unit circle, what's a nice number between pi and 5 pi over 4? Well, there's only one on here, right? 7 pi over 6. So we go to our function, our derivative function. If we were to punch in 7 pi over 6, we would end up with, let's go back up here for a second, 7 pi over 6. I'm going to use this equation. Here's my derivative, okay? So I need the cos of 7 pi over 6. I'm going to square that, minus the sine of 7 pi over 6. And again, we're going to have to square that. And remember, all I really care about is my signs, okay? Not necessarily the values. It's about the signs. So what's cos 7 pi over 6? That's root 3 over 2. And 1/2 is the other one. So if we were to put those in, we get negative root 3 over 2 squared minus 1/2 squared. So in other words, we get 3/4 minus 1/4. Oh, that's a positive. Okay, if we try the next one, 5 pi over 4 and 7 pi over 4. What's the number between those two things? Well, a nice one might be 3 pi over 2. Let's try that one. Go back to our question. 3 pi over 2. We're going to change all these little pieces here. See what happens. And again, we're only worried about our signs. So 3 pi over 2. 3 pi over 2. What's the cos at that point? Cos is 0, and sine is negative 1. So cos is 0 and negative 1. So we'll get 0 minus 1. Oh, it's a negative. Just guessing. I'm predicting the last one's probably going to be positive, but let's test it out. Something bigger than 7 pi over 4. So like 11 pi over 6. We'll get root 3 over 2 and negative 1/2. So root 3 over 2 and negative 1/2. And if we square those things, what happens? We get 3/4 again, minus 1/4 again, which is 1/2. So what are increasing and decreasing things? We know the function is increasing from pi to pi over 5 pi over 4, and it decreases. So in other words, there's a max there. And it increases again, so there must be a min there. Okay, that's the end of this unit. That's the end of this course. That's everything we need to know about trigonometric functions, how we can analyze them using some calculus, find maximums and minimums. Okay, some homework questions to try. We'll do a review, we'll do a test, and then we're on to the exam review for this section of the course.